After the long summer break, we are now back and into our usual job of evaluating integrals that no one really cares about. It doesn't have really many applications, but I am curious, and that is why I am doing it. Today we have quite a interesting looking integral, if I have to say so myself, where the top bound c satisfies the integral from 0 to c of x to the x is equal to 1. Now, the question of whether or not c can be expressed as a closed form, I don't think so. But we have set the definition, and now we're going to evaluate this integral. And I think it's actually quite a cool result, actually. And this fact definitely helps it. So the first thing we're going to do is we're going to realize that the main problem with this integral is this 0 to x of t to the t dt thing. And we can get rid of this by doing integration by parts. So this is going to be equal to the integral from 0 to c. 1 over x we're going to write as the derivative of natural log x. And then this integral will keep it the same, t to the t, dt, dx. And now we're just going to do integration by parts, basically. So, natural log of x here, integral from 0 to x of t to the t. This is from 0 to c. And then now, minus integral from 0 to c. The derivative of this integral is going to be just x to the x, because it's just this function, plug in x, so we have x to the x here, times this, which is going to be natural log of x dx. Now, we're going to look at this one part at a time. So for this one, this natural log of x times an integral from 0 to x thing, first of all, no, that's a t. First of all, we know what happens when we plug in c to this thing, because this is going to be 1, this is going to be natural log of c, so we have natural log of c minus whatever happens when x goes to 0. Now, you might recognize this as in 0 times infinity sort of thing, and we're going to just solve that here. We have the limit x approaches 0 of, we have natural log of x times integral from 0 to x of t to the t dt. Now, you could do the standard way of evaluating limits, or you could realize that the graph of t to the t looks kind of like this. It starts from 1, it goes down, and it goes up again. And this is useful because if we're taking x to be 0 and how do I explain this? When x is approximately 0, t to the t is approximately 1. Because what we're really saying is that this is the derivative of this function. So as x approaches 0, this is going to be the derivative is going to be approximately 1. So essentially, when x is small, this is approximately equal to just x. Now, obviously, you could do the standard L'Hopital method, but this is probably a much more easier way to represent this, because once again, it's just integrals, antiderivatives, and such like that. So if we have our approximation here, this is going to be just equal to the limit as x approaches 0 of x times the natural log of x. I have inside information that tells me this is equal to 0, but I'm going to evaluate this anyway. Now, if you were to try and do this using the L'Hopital's method, you will get something similar to this. But, as you will soon find out, this is equal to 0. And so, the final answer is the same. So how are we going to do this? We're going to, first of all, we're not going to apply anything. This x needs to go to the denominator. So this is equal to the limit x is equal to 0, natural log of x over 1 over x. And now we're going to take the derivative of both sides. So we have the limit x equals to 0 of the derivative of natural log is 1 over x. And then for this one, it's going to be negative 1 over x squared. Now, this negative we can move to the outside. And now 1 over x and this will just cancel. So we have basically 1 over x. and that's going to be x to the negative 1 to the negative 1. Negative 1 times negative 1 is going to be positive 1. And so now, we just get the limit of x as x approaches 0, which is going to be 0. So we have negative 0, which is going to equal to 0. Okay? So this limit is equal to 0, which means that this part is just natural log of c. Now for our second bit, which is going to be the integral. The integral from 0 to c, x to the x, natural log x dx. What we're going to do is we're going to write natural log of x as natural log x plus 1 minus 1 dx. Now this will come in handy in a little bit, because once we separate this, we can separate it in two parts. So integral from 0 to c of x to the x times natural log of x plus 1 dx, and then minus integral from 0 to c of just x to the x dx. Now this bit we know is just 1, but what about this bit right here? Now this bit is kind of special, because this is just the derivative of x to the x. Alright? So we're taking the antiderivative, or the integral, of the derivative of x to the x, and that's pretty easy. All you have to do is just plug in c minus plug in 0. So here, for this integral, all we have is c to the c minus, and we're gonna just set 0 to 0 to be 1, because I don't want to get myself into that much complications right now. So minus 1 again, that's going to be equal to c to the c minus 2. Alright, that's all very good. We have everything we need. So we just plug in that, and we get, should I write? Yeah, I should write the original equation, just so we have completeness. 0 to c 1 over x, integral from 0 to x, t to the t, dt dx is equal to, here we have natural log of c minus c to the c, minus minus is going to be plus, so we're going to have 2, positive 2, plus the natural log of c minus c to the c. And that is it. I think that is quite the interesting solution, and I don't think we could have got that if we don't have this special thing, this special equation. Now, is this c evaluatable using standard functions? I don't think so, because, well, this antiderivative doesn't normally exist anyway. We only got around that by, first of all, setting this to be 1, and also manipulating our expression here to give us this. Yeah, but I think this is very cool. It's a different sort of integral, you know, and I feel like the integral, it doesn't seem possible, but it's possible, and it's very well made answer. So that's all I'm gonna say for today. Thank you guys for watching, and I'll see you guys whenever I upload next, because honestly, I don't actually know when I'm gonna upload next. But I hope you guys have a good day, and I'll see you guys next time.